Greetings, Mathophiles. Welcome to a video on integration in which we will look at long division as a way of re-expressing improper rational functions so that they can be integrated more easily or integrated at all. We'll have two examples, the first of which you'll see on the screen. It's the integral of 2x cubed plus x squared minus 22x plus 7 all over x minus 3 dx. Probably the first thing you want to do is check to see whether x minus 3 is a factor of the numerator, because if it is, you divide and you get to integrate a polynomial and life is good. But if you plug a 3 into that numerator, you find that it comes out to be a 4 rather than a 0, and so fans of the factor theorem will know that means x minus 3 is not a factor of the numerator. So what we're going to do is we're going to go ahead and divide the numerator by the denominator, and then with luck, we'll have this integrand in a form that will allow us to get after it without too much difficulty. So I'm going to do the division synthetically. One hopes that if you are watching a calculus video on integration, that this is a technique that you've seen before. So I have the 3 from the x minus 3, and then I have the coefficients in the numerator, the 2, the 1, the negative 22, and the 7. Bring down the 2. 3 times 2 is 6 plus 1 is 7. 3 times 7 is 21, minus 22 is negative 1. 3 times negative 1 is negative 3, plus 7 is 4. And so that tells me that this is the integral of 2x squared plus 7x minus 1 plus 4 over x minus 3 dx. Now, this remainder term may or may not be easy to integrate. This one happens to be, except for that constant 4, this is just a natural log. There's no chain rule because there's nothing multiplied by the x. So I can go ahead and integrate term by term. This is 2/3 x cubed. This is 7/2 x squared. This is x. This is 4 ln absolute x minus 3, and of course we need a constant of integration. Not so tough, right? You have to know how to synthetically divide, or failing that, you have to know how to long divide. But this process takes that initial integral that we began with, that's pretty intractable with most reasonable techniques, and allows you to re-express it in a way that permits you to get to a result. Here is our second example, the integral of 2x to the fourth minus 5x cubed plus 3x squared minus 5x plus 7 all over x squared plus 1. And we have here a quadratic divisor, which complicates things a little bit. It's not factorable there down below, and so we're not going to be able to use synthetic methods. We're going to have to just gut it out the long way, and so we'll go ahead and do that. So my divisor is x squared plus 1. My numerator is 2x to the fourth minus 5x cubed plus 3x squared minus 5x plus 7. And here we go. If I divide 2x to the fourth by x squared, I get 2x squared. And if I multiply around, I get 2x squared times x squared is 2x to the fourth. 2x squared times 1 is 2x squared. And just as you would, I don't know if anybody learns how to long divide integers anymore, but just as you would in long dividing integers, you would want to make sure that you had the orders of magnitude, the powers of x in this case, in the numerical instances, the powers of 10, lined up. Now we're going to subtract. So we've got negative 5x cubed plus x squared minus 5x plus 7 left over. I divide the negative 5x cubed by x squared, I get negative 5x. Multiply around, negative 5x cubed minus 5x. Subtract x squared plus 7. X squared divided by x squared is 1. 1 times x squared plus 1 is x squared plus 1. I'm left with 6. So my quotient at the end of the day is 2x squared minus 5x plus 1 plus 6 over x squared plus 1. And that might look a trifle grim, but it's something that we're going to be able to handle. So this integral that we started with is now the integral 2x squared minus 5x plus 1 plus 6 over x squared plus 1 dx. Now, this is just, these first three terms are just polynomial terms. What about the 6 over x squared plus 1? Well, aside from the constant 6, that's the derivative of the inverse tangent. So we'll just happily go through term by term anti-differentiating. This is going to be 2/3 x cubed minus 5/2 x squared plus x plus 6 inverse tan of x plus a constant of integration. Now, we sort of lucked out, right? In our divisor, the x squared plus 1 set us up for the inverse tan. Now, if you had an ugly remainder term, there are things you can do. You could maybe approach it using partial fractions if you know how that works. But I just wanted to have a couple of examples that illustrated the process itself, and so I sort of rigged the remainder terms to be pretty tractable. But I hope this gives you a good introduction to this method of re-expressing integrands in situations where we have improper rational functions. Happy mathing.